Hello. Good morning. Welcome to the last day of classes for us. Last good morning, Michael. Last one. Okay. How goes it, everybody? All 7 of y'all here. Let's see where section H is in filling out their course evaluations. Good morning, Ryan. Oh, snap! So section H is at 55%. Good morning, space engineering student. Section H is at 55%, so 32 of you guys have filled out the evaluations. You need another 13 people, approximately, which I know all of you guys that are here have already filled it out. So poke everybody that you know, and I'll post it on Discord later as well. Yeah, so make sure you fill out the course evaluations for the extra 1%. EAS 202 project is over. That's submitted. That's awesome. How long was your document? Yesterday was Star Wars Day. Something I always forget until I go on social media and it proceeds to tell me. 13 pages, that's not too bad. That's not too bad. I mean, like, a 13-page, oh gosh. I'm not gonna lie, writing is the worst. Writing's the worst. Like, a 13-page English paper sounds terrible. A 13-page engineering report sounds okay to me. When I wrote my dissertation, I think it was 130 pages, something like that. But life gets easier when you have results in there. So, I mean, if you think about your EAS 230 final report, it was probably decent. It was probably a decent length. But how many of that was results? I don't know. Ryan. So, that's a really good question. So, under final exam... Under the final exam folder on UB Learns, you will see the practice problems that we're going to go over today, or at least as many as we can. You will see the recommendations for how to approach the exam on the day of. And then you should see the Zoom link. So if you are taking the normal exam at the normal time, you should see something called Zoom link. If you are taking the makeup, you should see Zoom link makeup. If you see, like, you should only see one. Ryan, do you see more than one? That means something's wrong on my end. But you should see, oh, dang it. You should see only one Zoom link. There should be a normal Zoom link if you have extended time, or if you are taking the makeup. Okay, thank you, Ryan. Thank you for letting me know. I will adjust the groups on my end and fix that. That's good to know. UB Learns is not very good at telling me what you guys see. Like, I really wish there was a better, like, student view of, like, what if I was in this group, or what if I was in this group, all that fun stuff. The exam is 2 hours to do everything. So 2 hours to do the problems and submit them. So if you look at the Zoom link, it says you have 1 hour and 5 minutes to complete the exam, plus 15 minutes to submit. The exam questions will be posted on UB Box, so you manage your time. So you have 2 hours to complete, because the submission link disappears at 2 o'clock. So make sure you allocate your time and all of that fun stuff. Okay, so it is 11:30. Let's go ahead and start our last day. So today I am going to go through practice problems that were posted. These practice problems are posted under final exam. You'll see them. The solutions are going to be posted at midnight tonight, so you'll have access to those. Make sure you use the practice problems as practice. But just before we do that, I want to go over some things I recommend about getting ready for your exam. So on your exam day, come early, click on that Zoom link. That you should see only one of them. I will double check to make sure everyone sees one. And log into UB Learns, log into UB Box, log into UB Zoom, all of that fun stuff. You can use your notes, you can use anything on UB Learns, like all of that material. You can open up Matlab if you want to use that. You shouldn't need anything beyond that. If you are really lost, then you didn't study enough and you should be in trouble. But you have access to all of that. Make sure you have your camera posted behind you so we can see all of that fun stuff. But log into UB Zoom and take 6 sheets of paper. So 6 separate sheets. You'll write, there's 6 questions on the exam, so you have 1 question or 1 sheet per question. Write your name at the top of all those sheets, just so that we can see that. And then you can go ahead and start your exam. So there are 6 questions. They will be linked on UB Box, so open up all of them in a new tab. If you don't open them in a new tab, that's fine. Just go back to UB Learns and you can see your exam again. But open them all right away just to save your work. And then you start. So let's go through some practice problems. So I got through 4 of them this morning with section H, so I'm assuming I will get through the same 4. I will post a video showing the remaining solutions at the end. Michael, that's a good question. You will submit 6 PDF, or you will submit 1 PDF containing all of your solutions. I don't know if the graders are like that, or the TAs. I don't care. 1 PDF. 1 PDF. Make sure all of your problems are there. Really, make sure all of your problems are submitted. Make sure we can find them. That's the big key. If you want to submit 6 PDFs, to be honest, I don't care. If you think that's easier, do that. Just make sure all of your problems are there and we can easily see them. So if you're submitting 6 PDFs, 1 for each problem, I'm assuming, make sure they're labeled problem 1, problem 2, problem 3. Just make sure all of it is submitted. Make sure it's easy to find. That's really what I prefer. Good question. Didn't think about it. Didn't really. I mean, I always assumed 1 big PDF. Didn't even think that it might make sense to do 6. But make sure all of your problems are there. Everything's submitted. Okay. So, practice problems. So all the practice problems are there. It's a good indicator of what kind of problems you're going to see on the exam. There are 6 of them there. I did them all this morning and checked all of my solutions in Matlab and corrected an error in the solution set. And it took me maybe an hour to do all of that fun stuff, which gives me confidence that you guys will do fine on the exam. Keep in mind, when you are going through the exam, process matters most. So if you don't know what to do, start by just writing down your process. What would you do normally? So let's go ahead and start. So it says consider 3 vectors in R4. R4 means that they have 4 numbers in each vector. These vectors are placed in the rows of a matrix. So essentially, we don't know what these vectors are, but they would be placed in the rows of a matrix. Doesn't really matter what they are. And the rank of this matrix is equal to 2. Okay, so given that information, we are asked to determine, is the set of vectors linearly dependent or independent? So for this one, the rank is equal to 2, but there are 3 vectors. So if I'm looking at the rank, that means 2 of these vectors are linearly independent. So it might be this one and this one. Oops. It might be this one and this one. It might be this one and this one. It doesn't matter. 2 of them are linearly independent. However, when we're talking about dependence and independence, we want to talk about the entire set. So the entire set, all three of them, are considered linearly dependent, because only two of them are linearly independent. So two of them are independent, all three of them are linearly dependent, because rank of A is less than the number of vectors. That says vectors, not vectors. Or rows. So that's why they're linearly dependent, because in this instance, the rank of A is less than the number of vectors or number of rows. So for part B, what is the span of the three vectors? This is a typo, 3 vectors. So my span formula is going to be a blank D space in R blank. Oops, it's not a blank. This blank here is the space the vectors live in. They each have 4 numbers, so it's an R4. This blank here is the number of linearly independent rows, or the number of linearly independent vectors, which comes directly from our rank. So this here is a 2. So my answer is a 2D space in R4, or a plane in R4. And then C. True or false, none of the vectors can be written as a linear combination of the other 3. That is false. By definition, linear dependence means that my vectors are linear combinations of the others. So I technically could have written this set of vectors as C1 V1 plus C2 V2 plus or equals V3. I don't know what my constants are. I don't know what C1 and C2 are, but they're not 0. By definition, this is linear dependence, where C1 and C2 are non-zero numbers. Okay, that's A, B, and C. It's a 2D space because 2 of them are linearly independent. Because my rank is 2. So this number comes from however many are linearly independent. This number comes from the space they live in. So for R4, it's either going to be a 1D space in R4, or a line, or a 2D space in R4, which is a plane, or a 3D space in R4, which is a cube, or a 4D space in R4, which is all of R4. Those are my options for a set of vectors in R4. This first blank is determined by the number of linearly independent vectors there are, which is determined by rank. We know that C1 and C2 won't be 0 because they are dependent. So if C1 equals C2 equals 0, then they would be independent. C1 equals C2, or C1 is not equal 0 and C2 is not equal 0, then they are dependent. So these are my options. We know it's not this option because they're not independent, so therefore it must be this option. Okay, D. Determine the values of A, B, and C such that W equals U plus K, V, where K is a constant. So if we look at these vectors here, these vectors, we have A, B, and C in there. You'll see that in a lot of these problems, you will see a variable that's used instead of a number. Do not freak out about it. Pretend that's a number. Just be like, oh, yeah, A is just another number in my vector. Doesn't really matter. Keep solving it as if you knew what that number is. So here's my equation. W equals U plus KV. So U looks like this. Plus KV equals W. Typically what happens, or what should happen, is as you are solving these problems, there will clearly be a set of equations that you can use to solve for one of your constants. So in this instance, solve for A, B, C, and K. So this first equation tells me that 0 or minus 2k equals negative 2. And here we can easily see what k is. This tells me that k equals 1. I didn't have to solve for k. That wasn't part of the problem. But I need it in order to solve the rest of the equations. So the second equation tells me that a plus 3k equals negative 2. Or that a plus 3 times 1 equals negative 2. And I can solve for a as negative 5. This third equation tells me that negative 1 plus kb equals negative 2. I plug in 1 for k, and I can see that b equals negative 1. And then this last equation tells me that negative 2 plus 0 equals c, or c equals negative 2. So we can see that I easily can solve for a, b, and c by just plugging in everything into here. Yes. And then my last E for part E. It says determine values of a, b, and c such that the three vectors are orthogonal. So this is a different set of a, b, and c. So this a, b, and c correspond to this linear combination. So I'm determining a different set such that my vectors are orthogonal. Whenever you see orthogonal, you should be thinking that the dot product is equal to 0. So v1 dot v2 equals 0. This is what we're thinking about when it comes to orthogonality. They're perpendicular. The dot product is equal to 0. So if all three of the vectors are orthogonal or perpendicular, that means that u dot v equals 0, v dot w equals 0, and u dot w equals 0. So I'm going to take the dot product between all three of these, set it equal to 0, and I should be able to find a, b, and c. So the dot product between u and v looks like this. 0 plus 3a minus b plus 0. Set that equal to 0. The dot product between v and w looks like this. 4 minus 6 minus 2b plus 0 equals 0. So set it equals 0. Dot product between u and w looks like this. 0 minus 2a plus 2 minus 2c. Set that equals 0. Use these equations to solve for a, b, and c. Using this equation, I can see that b ends up being negative 1. If I plug that into my first equation, I end up with a equal to negative 1/3. You'll want to show your work for that. I'm just jumping right to the answer because of time. Same thing here. If I plug in a, I end up with c equals to 4/3. So given a, b, and c, with these values, that means u, v, and w are going to be orthogonal to one another. They're all perpendicular. And there we go. I have my solution for problem 1. If you wanted to check your solution, if you wanted to check your answer with Matlab, you would do something like this. So when you're checking your answer with, so first of all, exam strategy, solve through all the problems first. Go through all the problems, solve them. If you have time at the end, then plug your answers into Matlab. When you're plugging your answers into Matlab, don't worry about trying to get Matlab to find the answer for you. Just plug in what you got and check to see if it works. So I got a to be negative 5, b to be negative 1, and c to be negative 2 for part D. And then k equals 1. Here's UVW, and then I'm just checking to see if U plus KV equals W. And note, W ends up being negative 2, negative 2, negative 2, negative 2. And then my answer also ends up being negative 2, negative 2, negative 2. So I'm checking to see just if it matches, if it works. And here it worked. Same thing down here. I got A to be negative 1/3, B to be negative 1, and C to be 4/3. Those show up in UVW, and then I just find the dot product between the three of them. So dot product is 0, dot product is 0, and then the dot product is practically 0. The issue with this one is we've got 1/3 in there. For some other reason, the computer does not like 1/3. It cannot handle infinite, like the number going on to infinity. So there's rounding error, but it's practically 0. So here it's 0. So the dot product between all three of these is equal to 0. So they're all orthogonal to one another. So don't worry about Matlab trying to get the answer for you. Just plug in what you got and check to see if it works. Okay, that's problem 1. Let's move on to problem 2. Problem 2 says consider a 5 by 5 matrix. You will not see a 5 by 5 on the exam. You'll see 3 by 3s and maybe a 4 by 4. A 5 by 5 is bigger. But if you can do it with a 5 by 5, you should be able to do a 3 by 3 or 4 by 4. 2 by 2s are a little small for the exam. Okay, so it says consider a 5 by 5 matrix A, and it gives us A. Determine the value of little a. So here, once again, I have that unknown variable that shows up in this matrix. Don't freak out about it. The reason why it's there is so that you just don't plug everything into Matlab. So you need to solve for it, and then you can plug things into Matlab. But here we have this variable. So I need to find a value for a such that the determinant of the inverse of this matrix is equal to 1/8. Okay, so the determinant of the inverse of a equals 1/8. If I think about my determinant properties, that means the determinant of a is going to be 8. So the determinant of this matrix should equal 8. Okay, that's great. Oh, look, that's what the B answer is. So I've already found my answer for B. If the determinant of A is 8, I can figure out what C is. I don't need to find the rest of A at the moment. The determinant of 2A is going to be 2 to the 5th times the determinant of A. So if I multiply this row by 2, 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 so if I multiply the entire matrix by 2, I'm multiplying the determinant by 2, 2, 2, 2, and 2, 1 for each row. So it's 2 to the 5th times the determinant of A, which ends up being 32. So 2 to the 5th is 32, times 8 is 256. So I found that determinant. And then for part D, the determinant of 2A times A inverse is going to be the determinant of 2A times the determinant of A inverse, which is 256 times 1/8 equals 32. So without even knowing what A is, little a, I can still find the answers for B, C, and D here. All with determinant properties. So if you think about your determinant properties, just keep them in the back of your mind. Determinant of A inverse equals 1 over the determinant of A. If I multiply a row by a constant, I multiply the determinant by that constant. If I multiply the entire matrix by that constant, I am multiplying each row by the constant, hence the 5th. If I multiply two matrices together, the determinant is going to be the determinants of those two matrices multiplied together. Okay, so I've got that. So I still need to figure out this value, though. So it says to easily solve this problem, you should reduce the matrix to REF, my triangle matrix, where I have a lower triangle of zeros, which is great. For the lower triangle of zeros, the determinant is equal to my diagonal multiplied by each other. So I'm going to go ahead and reduce my matrix to REF. Pay attention, though, that when we apply row operations to this matrix, it's going to change the determinant. Okay, so I want my lower triangle of zeros. The first thing I am going to do is I'm going to swap rows 1 and row 2. So that means row 1 looks like this. And I'm doing that because I want this 1 and this 0 to be in row 2. I don't want it to be in row 1. I see your question, Cupcake Panda. I will answer it in a minute. Okay, so if I swap rows 1 and rows 2, that means my determinant changes the sign. So the determinant of this matrix, we'll call it A2, equals, we'll call it, the determinant of this matrix, A new, is going to be -8. So I just need to keep track of if my original determinant is 8, if I apply row operations to get it into REF, how does my determinant change? So if I swap 2 rows, my determinant changes from a +8 to a -8. And then I'm going to do some elimination steps. I'm going to say row 3 equals row 3 minus row 1. And row 5 equals row 5 plus 2 row 1. So I'm trying to make this a 0 and this a 0 to get all the zeros in my first column. So when I do this row operation, I get 2 minus 2, 0 minus 0, -2 plus 1, 0 minus 0, and 0 minus 1. I'm just showing the math over on the side here so I can easily keep track of what I'm doing. I can easily keep track of what my signs are, how they change, all of that fun stuff. So make sure you're showing your work in some way, shape, or form. Keep track of what you're doing. For this one, I get -4 plus 4, 0 plus 0, 0 minus 2, 0 plus 0, and then 2 plus 2. So my new matrix ends up like this. Whoop, that one changes. I get 0, 0, -1, 0, -1, and then 0, 0, 0, a 0, and then 0, 0, -2, 0, and 4. Note, these row operations are row operation 3. My determinant doesn't change, so this is still going to be -8. So going from here to here, I just did row operation 3. My determinant doesn't change. So from here to here, it became +8 to -8. From here to here, it didn't change. I have one more row operation to make this a 0. So I'm going to say row 5 equals row 5 minus 2 row 3. You do not need to do the same row operations as me. These are the ones that I'm choosing. You just need to make sure you're keeping track of how your determinant changes. How your determinant changes given the row operations you do. So let me do this last row operation and then I will answer your question, Cupcake Panda. So here I end up with 0 minus 0, 0 minus 0, -2 plus 2, 0 minus 0, and then 4 plus 2. So I get this final matrix. I end up with 0, 0, 0, 0, and 6. So going from this matrix to this matrix, I just use row operation 3 again. So my determinant doesn't change. Okay, so a little bit of review. If you swap rows, determinant of A becomes change the sign. If you multiply a row by a constant, then the determinant of A is multiplied by that constant. If you do your elimination step, determinant of A doesn't change. I know my handwriting is very sloppy there. But if you swap rows, your sign changes. If you multiply a row by a constant, you multiply the determinant by that constant. If you do just your elimination step, just row operation 3, where we say row x equals row x plus some multiple of row y, like we did for LU factorization, then your determinant doesn't change. So here's where we change the sign. These ones, it doesn't change. This here is an example of multiplying a row by a constant. So if we multiply this whole determinant, or this whole matrix, by 2, so I have 2a, I am multiplying row 1 by 2. I am multiplying row 2 by 2. I am multiplying row 3 by 2. I am multiplying row 4 by 2. I am multiplying row 5 by 2. So I'm multiplying 5 rows by 2. Row 1, row 2, row 3, row 4, row 5. Which means that I'm multiplying my determinant by 2 here, 2 here, 2 here, 2 here, and 2 here. So 2 to the 5th, 1 for each row. That's your answer to your question, Cupcake Panda. It's just a modification of where we multiply a row by a constant. Okay. So back to over here. So I've got my determinant, or I've got my matrix in REF. I've followed my determinant as I've applied row operations. Yes, Flora, yep, that's exactly what it is. So for K times the determinant of A, that's if you multiply a one row by a constant. If you multiply the entire matrix by that constant, then you need to raise your constant to the number of rows you have. Okay, so the determinant of this new matrix should be -8. So this is a triangle matrix, which means my determinant of this new one is going to be 2 times 1 times -1 times A times 6. And this should equal -8. So I multiply all the values along my diagonal. Cupcake, I don't... This is recorded, so keep track of the time. It's 33 minutes in, so 30 minutes in, you can go back and watch it. I just want to get through 4 problems. So A here ends up being, so -12 equals -8. A ends up being 8 over 12, which is 2/3. There we go. There's my value for A. I don't need to worry about flipping the sign or anything because I've already done that here. The determinant of this matrix is 8. But I don't have that matrix anymore. I have this matrix, then this matrix, then this matrix. So I just follow my sign through, follow my determinant through. The value of A I didn't modify A. A is still just a number that appears in my matrix. So whatever I find A down here is going to be the same A as it is up here. I've already accounted for my determinant changing with my row operations. So A ends up being 2/3. And there we go. I finished up this problem. Once again, I did it backwards. We did B, C, and D first, and then we went back and finished A. Yep, so you can find the determinant of any size matrix by REF and then multiplying diagonals. Keep a track, though, of how that determinant changes. So if you started with this matrix, if you started here and knew the row operations you applied, you would need to work your way back up. So if this matrix has a determinant of -8, going this way, this one will also have -8 because I only used row operation 3. This one will also have -8 because I only used row operation 3. But then going back up to A, I swapped rows. So going from this one, this matrix here, to A, it would go from -8 to +8. So it just depends on which direction you're going. Okay, if you want to check your answers with Matlab, it would look like this. So once again, just plug in your answers. I got A to be a value of 2/3. Here's what my big A matrix is. I'm checking what my determinant of A is, what my determinant of the inverse of A is, what my determinant of 2 times A is, and what my determinant of 2 times A times the inverse of A is. So there we go. So I check the determinant of A is 8, the determinant of the inverse is 1/8, The determinant of 2 times A is 256, and the determinant of 2 times A times the inverse of A is 32. So don't worry about letting Matlab find the answer for you. Just plug in your answers and check to see, okay, yep, that works. I got the right answer. If you didn't get the right answer, so this one had an error in the solution. So I had to go back and just double check that everything was correct. I got the wrong answer because I did a minor math mistake. I had an 8 here instead of a 6. But once again, if you show all your work, it's easier to find your mistakes. There's problem 2. It sounds like problem 2, there's a bit of a hang up for you guys. So go solve it yourself. Come back to the video and see where your gap is, what information you're missing. Okay, moving on to problem 3. Okay, we've got 20 minutes left. Moving on to problem 3. Woohoo! Let's solve some systems of equations. Okay, given the following system of equations, write it in the form of ax equals b. I can do that. I've been doing that for a while now. A11. Note, there's a variable that shows up. Once again, ignore it. Don't get caught up in the fact that there's a number there that you don't know. Just ignore it and keep moving on. So 5, -2, 1, -2, 1, 4, 3, -1. X looks like this. B looks like this. Then it says, find the values of the cofactor C11, C12, and C13 of matrix. So anytime you are finding the cofactors, so for C11, we're finding the cofactor for the 1, 1 position, so row 1, column 1. Take out the row and the column it's in. Find the determinant of the remaining numbers. And then adjust the sign as needed. So for the 1, 1 location, it's a plus. So here I end up with 2 minus 3 or -1. For C12, same thing. For the 1, 2 location, cross off the row and column you're in. Determinant of the remaining numbers. Come on, pen. Adjust the sign. So here I end up with -1 minus 4 or +5. For C13, take out the row and column it's in. Determinant of the remaining numbers, adjust the sign. And then I get 3 plus 8 or 11. There we go. I found my cofactors. It didn't even matter what A11 was. Like, I didn't even need that number. Moving on to part C. There we go. Find a value for A11 so that the determinant of A is equal to 1. So I'm finding it such that determinant of A equals 1. So I know what my determinant is. Now I need to figure out how do I calculate my determinant. There's a couple ways we can calculate the determinant. We can do cofactor expansion along any row or any column. We can do our modified fish method. I'm going to do cofactor expansion along row 1 because I already have my cofactors along row 1. So A11 times its cofactor, which is -1, plus 5 times its cofactor, which is 5, plus -2 times its cofactor, which is 11, equals 1. So my determinant should equal 1. So here's my equation for determinant. Here's what my answer should be. Keep in mind, I did cofactor expansion. I already adjusted for the sign when I found my cofactors. So make sure of what you've already done versus what you need to do. So it turns out when I solve for A11, it ends up being 2. Woo. I mean, technically you could do REF, but that's the long way to do it. You already have the cofactors found. So when it comes to finding the determinant, you really want to use the simplest method. So if you're doing cofactor expansion, do it along the row or column with the most zeros. If you already have a triangle matrix, or if you're told to get it into REF, then you would multiply along your diagonals. For this one, there's no method you're told to use, but you're already calculated cofactors, so it implies that it might be the easiest to use cofactor expansion along row 1. I would suggest not transforming it or not reducing it into REF unless you are told to, just for simplicity's sake. For this one, we don't know what A11 is, so it would show up in our equations. And we'll see in the next problem as well what it looks like to do row operations with unknown numbers. So for this one, it would just make it more complicated to do it, to reduce our matrix to REF. Okay, so now I want to answer this. If the system is consistent, it is. How many solutions for the system? Note my determinant of A is equal to 1. That's not equal to 0. Therefore, I have a unique solution in a consistent system. So if you go look at week E notes, you'll see that summary and that chart at the bottom that essentially tells us this answer. Our determinant isn't equal to 0. Therefore, A inverse exists. Therefore, we have a unique solution. Therefore, our equations are linearly independent. Our system is consistent. The rank of A is 3 for this system. The rank of AB is 3. All of that fun stuff we can determine, all because our determinant is not equal to 0. Okay, and then this one. Whoops. This one. Find a value of x1 using Cramer's method. So Cramer's method tells us that x1 is equal to the determinant of A1 over the determinant of A. I already know the determinant of A equals 1. Now I need to find the determinant of A1. The determinant of A1 is going to be the determinant of the matrix A, where column 1 is replaced by my B values. So here for column 1, my B values are -5, 3, -2. And then the rest of it just stays as A. 5, -2, 3, -2, 1, -1. So I need to find the determinant of this matrix, where this column comes from B and these ones come from A. You can use any method you want to find the determinant. I use the modified fish method. Used to be my favorite method. I'm much more equal among the methods now. But I'll use modified fish method. So I'm just going to write my values next to it and find my diagonals. This diagonal is -10. This diagonal is, this one first. Here we go. -10, -10. This one is -18. This one ends up being -15. This one is -15, and this one is -8. So the determinant of A1 is going to be -10 minus 10 minus 18 minus -15 minus 15 minus 8, or equal to 38, -38 minus -38 equal to 0. We get a 0 for a determinant, but that's fine. It's not a problem. It just means that for x1, we get 0 over 1. 0 over 1 is valid. x1 equals 0. And then I'm done. I can stop. So if the determinant of A equals 0, then we have a problem. If I end up with a determinant of A1 or A2 or A3 equals 0, that's fine. Not an issue. Because we end up with, our math still works. Our math still works. We end up with 0 over 1 versus something over 0. I was told the determinant should be equal to 1. So in the problem statement, it says Find a value A1 so the determinant of A is equal to 1. So I'm told it needs to be 1. So I'll make it 1. If you want, Danny, would it mean, so no, because the determinant of A is equal to 1. This is the one that matters. The determinant of A1 equals 0. This doesn't matter. I don't care. That's just a number that I'm using to solve my system. But since the determinant of A is equal to 1, it's not equal to 0, I get a unique solution, consistent system. If you end up with a determinant of A equals 0, then you either have a consistent with infinite solutions or inconsistent with 0 solutions. So if you end up with a determinant of A equal to 0, then you need more information. It's either consistent with infinite solutions or inconsistent with no solution. So there's problem 3. If I wanted to check my answers in Matlab, it would look like this. So I end up with A11 equal to 2. So once again, I'm just plugging in my answers. A11 equals 2. Plug in A, plug in B. Check to make sure my determinant of A is equal to 1. There's no easy way to find your cofactor. Like, you can't just say cofactor 1, 1. But what you can do is we know that the inverse contains our adjoint matrix, which is full of our cofactors. So here's what I can use to find the cofactors. And then here I'm solving my system, and I can check to make sure x1 is equal to 0. So if I do that, here's my determinant is equal to 1. Here is my matrix of cofactors. My cofactors along the first row of A are going to be the first column in my adjoint. So -1, 5, and 11, that matches what I got. And then here, x1, once again, it's not exactly 0 on the computer because of rounding error, but it's practically 0. So here it's 0. So I can check my answers in Matlab. Okay, we have 7 minutes to get through the next problem. So here it says, given the following system of equations, rewrite the system in matrix format and determine the following. So if you read through this problem, the key point for this problem is finding the rank of A and the rank of AB. If you are ever asked to find the rank of A and the rank of AB, skip finding the rank of A directly and jump straight to the rank of AB. So if I rewrite this equation, the system of equations, in augmented form, I get 2, 3, 4, 12, 1, -2, 1, 3, 4, -1, A3, 3, and B3. Okay, we have those unknowns in there. That's fine, not a problem. I need to find the rank of A and the rank of AB. So here for this first one, it says find values of A3, 3, and B3 such that both the rank of A and the rank of AB are equal to 2. Okay, so I'm just gonna start by, I know I need to find the rank, so I'm gonna find the rank. I don't know what A33 and B33 are yet, but hopefully somewhere I get to a point where I can figure out what those are. So, first thing, when you're finding the rank, you want your lower triangle of zeros. So I'm gonna say that row 2 equals 2 times row 2 minus row 1. And that row 3 equals row 3 minus 2 times row 1. I would show my work. I'm not going to right now, just for simplicity's sake and making sure we get through with the problem. If I do those row operations, I end up with 2, 3, 4, and 12. Note when I do this one, I end up with 4 minus 4, -1 minus 6, A33 minus 8, and B3 minus 12. I don't know what those are going to end up being, so I'm just going to leave them in their equation form. Oops. So row 2 ends up being 0, -7, -2, -6, And row 3 ends up being 0, negative 7, A3, 3 minus 8, B3 minus 24. Oops. So I don't know what those are, but I'm just going to leave it alone for now, and hopefully something makes sense. Then I want to get, this is 0, so I'm going to say row 3 equals row 3 plus or minus row 2. When I do this row operation, I get 0 minus 0, negative 7 minus negative 7. And then, once again, I'm not working with regular numbers, but I'm still going to write out my equation. A33 minus 8 plus 2, and then B3 minus 24 plus 6. I end up with 0, 0, A33 minus 6, and B3 minus 18. So I'm stuck here. I'm stuck. So hopefully something makes sense moving forward. I've found as many zeros as I can find. So let's go back up and read the question. Find values of A33 and B3 such that the rank of A and the rank of AB are equal to 2. If my rank of A and AB are both equal to 2, I should end up with 0, 0, 0, 0 along the bottom. So this should be a 0, and this should be a 0, which means that A33 minus 6 equals 0, and B3 minus 18 equals 0. So here's where our equations come out. I know I'm expecting a 0 here, therefore A33 should be equal to 6. And B3 should be equal to 18. So there's my answer for A. If the rank of A is 3, and if the rank of A is 2, and the rank of AB is 2, I should end up with zeros along the bottom. Woohoo! I also know that if the rank of A equals the rank of AB, then my system is going to be consistent. If it's consistent, my options are either going to be one solution or an infinite number of solutions. In this instance, if I end up with zeros all along the bottom, I'm going to have an infinite number of solutions. That was not the infinity symbol. And we'll come back to this in a minute. Okay, so 1, and then 2. Find values of A33 and B3 such that both the rank of A and the rank of B are equal to 3. So if they're equal to 3, I'm going to end up with this situation. 0, 0, something, and then something. Some non-zero number, and then some non-zero number. I'm not told what those numbers are going to be, so I'll just make it up. I'll just say, what if they're 1? What if they're both 1? If that was the case, then A33 minus 6 equals 1, or A33 equals 7. No, there's an infinite number of options for this. I'm just picking one of them. And then B3 minus 18 equals 1. And B3 would be 19. Infinite number of options for that, I'm picking one of them. So if the rank of A equals the rank of AB, if they're both equal to 3, I'm going to have a consistent system again. And now I'm going to have a unique solution. So there's my answer for that. Consistent and unique. And then lastly, find the values of A33 and B3 such that the rank of A is 2 and the rank of AB is 3. This situation, I'm going to end up with 0, 0, 0 for the A side, and then some value for the B side. So I would end up with like a 1 here. Once again, infinite number of options. I'm just picking 1. So for that instance, then A33 minus 6 would be equal to 0. Or A33 is 6 again. And then B3 minus 18, let's just pick 1. So B3 would be 19. There's my C option. So if that was the case, then I'm going to have an inconsistent system, because the ranks are not equal to each other, and I only have, there's no solution. So identifying all of those scenarios. Find the rank, The rank of A is whatever shows up on this side. Come on, pen. And then the rank of AB is whatever shows up on the entire side, or the entire matrix. Then the last piece it says here, solve the system of equations for number 1. So in the instance that A33 equals 6 and B33 or B3 equals 18, I end up with this matrix. Where I end up with my row of zeros. That means I'm going to have an infinite number of solutions. Just keep going through to do Gauss-Jordan elimination. So I would make this a 0. So I would say row 1 equals 7 times row 1 plus 3 times row 2. If I did that, I would end up with this. Then I would divide this by 14 and this by -7, which gives me my final RREF form of 1, 0, 11 sevenths, 33 sevenths, 0, 1, 2 sevenths, 6 sevenths, and then my row of zeros. If I'm gonna write my system, my solution, I just write my equations. So here it tells me that x1 plus 11 sevenths x3 equals 33 sevenths. x2 equals 2 sevenths x3 plus 6 sevenths, or equals 6 sevenths. Come on. And then x3 equals x3. I don't have any information. That's my free parameter. So my solution is going to look like this. 33 sevenths minus 11 sevenths x3. 6 sevenths minus 2 sevenths x3, and then x3. There we go. There's my solution. So if you're ever told to find the solution and there's an infinite number of solutions, you're not picking one unless it's an eigenvector. Just write them all in terms of your free parameter. And one last thing before we go. I know we're late, but one last thing. If you want to check your answers, Flora, I mean, you could have used back substitution, but there would have just, you would, I mean, it's really easier to do it with Gauss-Jordan, because otherwise you would have to substitute things in. Like you can't just write it as 2x1 plus 3x2 plus 4x3 equals 12. Like you need to get rid of the x2, only have it in terms of x3. So you would have to go back and substitute something in anyway. So it's typically just easier to just do Gauss-Jordan when you have an infinite number of solutions. Okay, if you wanted to check your answers in Matlab, it would look like this. So just plug in what answers you picked for A and B. So A was 6, B was 18. You can see RREF, rank of A, rank of AB. Clear my workspace, sorry about that. So we can see that REF, I end up with my row of zeros. The rank of A is 2, the rank of AB is 2. Same thing here. I end up with a 1 here and a 1 here. It's not 0. Rank of A is 3, rank of AB is 3. Perfect. And then same thing here. I end up with zeros just on my A side, a 1 on my B side. I get a rank of 2 and a rank of 3. I don't have a solution. Okay. Sorry about going late. I just wanted to make sure I finished up that problem before we left. And then we're done. I will create videos to go over solving question 5 and question 6 on the final exam, or on the practice problems. Those ones are a little longer, but I will post that video on UB Learns. And that is it. I will see you guys at the final exam. Good luck. One of your homeworks will be dropped before calculating your final, before your final grade. So if you want to estimate your grade and what you need to get on the final in order to get a specific grade, feel free, drop that lowest homework. It's going to be dropped by percentage. So it's not the smallest number, it's the smallest percent. So if you got 50% on a homework and then like 80% on the others, your 50% would be dropped. Any final questions? Okay. I will see you guys all at the final. Good luck, and I will fix that issue for the Zoom length. Have a great weekend, study a lot, get sleep. I'll see you guys on Tuesday.